Hey guys, this is Fendley. The word congruent means two figures that are exactly the same. They're the same shape and the same size. So for example, if I draw a little trapezoid here and I use my tool to click duplicate, well, I've got two identical trapezoids. So those two trapezoids are congruent. And so far in this chapter, we have looked at three types of transformations so far, and all three of those transformations were congruent transformations, which means that when you do the transformation, the two figures are congruent. The beginning figure and the ending figure are congruent. So far we've looked at translations. And the word to translate means to slide. Okay? To slide around. So you change the location, you move it up and down, but it's not changing the size or shape. So, the two figures are congruent. The second type of transformation we've looked at so far were reflections. The word reflect, just like it means in real life, it means to mirror or to flip. So if you take the trapezoid and you flip it upside down, right? If you reflect it across the x-axis, then you change the orientation, which is the direction that the figure faces, but you haven't changed the size or the shape. You've changed the location, you've changed the orientation, but not the same size or shape, so the figures are congruent. And then the last congruence transformation that we looked at so far were rotations. The word rotate means to turn. Right? So it can you move it in a circle around a point. Changes the location and orientation, but not the size or shape, so the two figures are congruent. In math, the word similar, it's a little different in math than it is in normal everyday life. In normal everyday life, the word similar means that's mostly the same, same but different. In math, similar specifically means that it's exactly the same shape, but it is a different size. Okay? The shape doesn't change, so as it gets bigger and smaller, it stays proportional. We only have one similarity transformation, and we call that a dilation. So the word dilate means to change size or to get bigger or smaller. To change the size. And if you have ever been to an eye doctor, when they put those drops in your eye and it makes your pupil get big, they call that dilating your eye, right? So it links back to everyday life. And if you guys have a cat, if you ever watch the cat do a little wiggle butt, right before it attacks, its eyes will get really big. The eyes dilate. So here in these two figures down below, we have originals and we have new figures. So how can I tell whether this is the original or this is the original? Okay. Notice that was tiny, let me zoom in, but notice the prime, right? This little apostrophe. That tells me that this is the original pre-image. And the apostrophe tells me, hey, this is the new image. Okay. Whereas on this yellow one, the one with the apostrophe is the new image. The one without the apostrophe is the original pre-image. Okay. So when something goes from small and gets bigger, that's called an enlargement. So small to bigger is called an enlargement. It gets larger, right? When you start big and get small, that's called a reduction. The size reduces. So big to small is called a reduction. Okay? When it gets larger, it's an enlargement. When the size reduces, it's a reduction. Okay? And we call the amount that it gets bigger or smaller the scale factor. So when we say that, maybe for example, we'd say that this safety pin, the new safety pin is, let's just make up a number, it's not accurate, but twice as large as the original safety pin, well then the scale factor is 2. If we say this diamond encrusted paperclip, this is actually diamond encrusted paperclip by the way, is half as big as the original diamond encrusted paperclip, then the scale factor is 1/2. So the amount that the size gets bigger, the amount that the size gets smaller is called the scale factor. And the simplest dilation rule is just to remember original times scale factor equals new. If you can remember this sentence right here, original times scale factor equals new, dilations are going to be easy peasy. We're going to use the letter K to represent scale factor because that's a lot of letters. And we're not lazy. We're efficient. So instead of writing the word scale factor every time, we're going to use the letter K to represent it. So let's look at a couple of examples. On this example on the left, we have the blue triangle PQR and the new triangle P prime Q prime R prime. Well, PR is 5, right? That was the original, was 5. The new scale factor, excuse me, not the new scale factor, the new side, P prime R prime, is 10. Well, 10 is twice as big as 5. So 5 times 2 equals 10. The scale factor is 2. And let's say we're using numbers that we can't just look at it and know, oh, I know what 5 times what is 10. Let's just look at another example. Okay, so 4 becomes 8. All right, so 4 original times scale factor equals mu. Original times scale factor equals mu. Oops. Well, 4 times k equals 8. I want to get k by itself. 4 times k, I do the opposite and divide. So k equals 2. Right? And then if I wanted to just verify that one more time, it works on all the sides. Right? PQ at 3 is going to become P prime Q prime 6. Okay. Well, 3 original side length times the scale factor equals the new side length. So 3 times k equals 6. Solve for k. That's multiplication. We're going to do the opposite and divide. Those are going to cancel out. We're left with k. 6 divided by 3 is 2. So the scale factor is 2. So triangle P prime Q prime R prime is twice as big as the original PQR. Okay. On the next one, you got to pay attention to which is the original and which is the new. Okay. Whenever you see the prime, that's new. Okay. Prime means that's the new. Without the prime is the original. So if I want to figure out what is the scale factor, it might be very tempting to look at this and say, oh, 3. No. Original, which is 12, times our scale factor equals new, which is 4. So 12 times what equals 4? Okay. We're going to do the solve for k. We have multiplication, so we're going to do the opposite and divide. And we're left with k equals 4 over 12. Now you guys have the option of plugging that in your calculator. But what are 4 and 12 both divisible by? Right, they're both divisible by 4. So 4 divided by 4 is 1, 12 divided by 4 is 3. So the scale factor is 1/3. This new triangle is 1/3 the size of the bigger triangle. So on the left, we had an enlargement because the triangle got bigger. And on the right, we had a reduction because the triangle got smaller. Okay? This rule works in the coordinate plane too. Original times scale factor equals mu. So if the original point, let's call it A, is at xy, we're going to multiply those coordinates by the scale factor k, and A prime is going to be at x times the scale factor and y times the scale factor. So for example, let's say that we're looking at point B at -3, 2, and it's dilated by a scale factor of 5, or by a factor of 5. Okay? Original B is at -3, 2, times our scale factor of 5. Okay? That's going to give me B prime at, well, -3 times 5 is -15. And 2 times 5 is 10. So B prime would be at -15, 10. Okay? Let's look at it in context. So it says graph triangle PQR with vertices at 0, 2. So P is at 0, 2. Q at 1, 0. And R at 2, 2. And its image after a dilation with a scale factor of 3. Okay, so I'm going to take each of those points. I'm going to take my original P and multiply point P by my scale factor of K. I'm going to say xy times k and give me my new point, which is going to be each of the coordinates multiplied by the scale factor. So the original point was P at 0, 2. My scale factor is 3, so P prime is going to, well, 0 times 3 is still 0. 2 times 3 is 6. So P prime is going to be at 0, 6. Okay. Do the same thing for Q. Q is at 1, 0. The scale factor is 3. So Q prime is going, well, 1 times 3 is 3. 0 times 3 is 0. Okay. So Q prime is at the point 3, 0. And then the last point R is going to be at 2, 2. So just multiply each of those coordinates by the scale factor 3. Well, 2 times 3 is 6. 2 times 3 is 6. So R prime is at 6, 6. So now, if you were to break out your ruler or Pythagorean theorem, you would notice that each of these sides are 3 times longer than their corresponding side. So PR is 2 units, and P prime R prime is 6 units long. Right? 2 times 3 is 6. Fun fact, in addition to being each of the sides being 3 times longer, it's also 3 times farther away from the origin. So for example, from the origin to point P is 2 units. From the origin to point P prime is 6 units. 2 times 3 is 6. So the scale factor affects how the side lengths, and it affects how far away it is from the center of dilation, which for our purposes is going to be the origin. We're just going to keep things simple and make it always the origin. All right, let's look at one more example here. So it says graph triangle PQR with vertices P is at 4, 6. P is at 4, 6. Q is at -4, 2. And R is at 2, -6. And its image after a dilation with a scale factor of 0.5. Okay? So 0.5 is going to be half the size of the original triangle. So let's look at this point by point. So again, original times scale factor, we're going to use k for scale factor, equals mu. Okay, so my original point was p at 4, 6 times my scale factor of 0.5. Let's just think half. What is half? Okay, equals my new point, so we're going to call that p prime. Well, half of 4 is 2, half of 6 is 3. So point p prime is going to be at 2, 3. Point q, so original times scale factor equals mu. So q is at negative 4, 2. Times, so original times scale factor 0.5 equals my new point, q prime. Half of negative 4 is negative 2. Half of 2 is 1. So q prime will be at negative 2, 1. And then the last point, r, is at 2, negative 6. So my original is at 2, negative 6 times scale factor 0.5 equals r prime. So half, original times half. So half of 2 is 1. Half of negative 6 is negative 3. So 1, negative 3 is r prime. Connect those dots. And the new orange triangle, p prime, q prime, r prime, is half the size of the original triangle, pqr. In addition, the distance from the origin to p prime is half the distance from the origin to p. Okay? Same thing for all of them. The distance from the origin to q is half the distance from the origin, from the origin to q prime is half the distance from the origin to q. Okay? So that's how you do dilations on the coordinate plane. Your original times scale factor equals mu. If it asks you to find the scale factor like it did up here, let's say, just for example, if I had been given the point p at 0, 2 and the point p prime at 0, 6, and they asked me to find the scale factor. So in our example, we told you the scale factor and you were finding the new coordinate. But let's say, for example, they said, hey, here's p prime. What is the scale factor? Well, we said 2 times the scale factor equals 6. 2 times the scale factor k equals 6. So the opposite of times is divide. Those are going to cancel out and we're going to be left with k. 6 divided by 2 is 3. Yeah? So original times scale factor equals mu. And that's pretty much all you need to know to dilate on the coordinate plane. Good luck, guys.